Now, what we found last time, remember, when we took the space-time that's warped, the idea seriously, what force did we find that it's a perfect model for? Gravity. Why? What was it about gravity that we found that it could perfectly model?
The acceleration was mass independent.
Right. Irrespective of whatever the mass is, because it's the space-time that's causing this phenomena, all masses will have the same result, they'll all have the same resulting acceleration. And that's exactly what happens in gravity. You take something, you let it go, it starts accelerating. Take any mass, they'll all accelerate with the same thing. Take any mass and let them accelerate, and let yourself accelerate, irrespective of your mass, you're all going to feel that you're inertial. So it's exactly the same thing. As you fall, other things that are also inertial particles, however, whatever velocity they're moving with in whatever direction, they all see each other with straight trajectories as they cross points. Right? For all these reasons, we know that free fall world lines are geodesics. They must be geodesics, and that's the geodesic properties you have for space-time. That quantity that tells you how the straightest lines curve is exactly the quantity that tells you how much free fall world lines curve when you look at it as though it's a flat spacetime. Then we said, okay, if that's the case, let's model gravity using this idea. We said that there was a, let's say, a spherical mass. It creates an acceleration field outside it of gm over r squared. We know that acceleration is simply, what is it geometrically? The acceleration curvature of the right, of the world line. The graph that you draw in this space-time graph, the world line, its curvature is exactly the acceleration. So we can have, instead of an acceleration field in the ordinary Newtonian sense, we have a world line curvature field. Which we then said, well, it's not really a world line curvature field. We went up to the next level and said, if there's a theory where you really can put a curvature onto time, a warping onto time, space-time, you're going to find some quantity in that curved space-time that describes how the straightest lines curve, which is exactly this. This quantity, which tells you in the differential geometry theory that's going to represent what we spoke about. Okay, again, you have these two pictures. You have the flat space-time illusionary picture where you think you can draw the axes in this way, and you end up with world lines that have curvature. And the world line curvature is simply the acceleration, gm over r squared. You really know that there's a warped space-time, and these lines are as straight as possible. So the warping of the space-time is given by this to some degree. And the curvature of the straightest lines, which is given by this in the geodesic equation, will have very close relationship to the curvature of the world lines when they look unstraight. Okay, is that particular point very clear? Because that's a crucial. Yeah? Okay, that's why this turns out to be the acceleration. Because the acceleration on the one hand is 0, and the world lines are straight because there's no acceleration. On the other hand, the world lines, of course, are not straight, they're curved. This is exactly the quantity that tells you where that comes from and how much it is. So this will be, what do you expect this quantity to turn out to be? This is kind of like a curvature of the geodesic in this curved space-time. It has to map directly onto, somehow, the curvature of the world line in the flat space-time illusionary model. The curvature there is gm over r squared, so we would expect that when you project this down to Newtonian, this will turn out to be gm over r squared. That's what happens. We have this picture of, in Newtonian physics, you have a force outside a mass, mm over r squared. We say take the equivalence principle seriously, forget about forces, talk about an acceleration field, just m over r squared. And then you know that whatever particle comes through, irrespective of speed and direction, you know what its acceleration is. Then we say, no, take that more seriously, space-time more seriously, and we'll call it a world line curvature field. Then we say, no, take the picture of warp time more seriously, and call it not a world line curvature field, but a space-time geodesic curvature field. When you measure the m over r squared outside this mass, what you're measuring is these gammas in your higher level theory, in your curvature of space-time theory. You're measuring this gamma. That's what this field is. Just that you see it as a world line curvature or acceleration, because you don't realize space-time is squared.